Okay, in this example, I'm asked to rewrite the expression using exponent properties. Now, I could do some other things first here, like rewriting 81 as a number to a power, but I think I'm just going to stick with exponent properties to start with and take that as far as I can go. Since these two numbers have the same base, we can add their exponents due to the product of powers property. So we'll have 81 to the power of 5 over 6 plus negative 1/3. Now when I add fractions, remember you have to have a common denominator. The common denominator here would be 6. So just off to the side, it would be 5 over 6 plus, in terms of 6, 1/3 is going to be 2/6. So we'd have negative 2/6. And since they now have a common denominator, we just add the numbers across the top, keeping our denominator the same. So we'd have 3 over 6, which reduces to 1/2. Now that we have this, we're going to apply the property dealing with fractional exponents. It just says that we can rewrite it as an exponent and a root or an index. So rewriting it as a radical here. So the index will be the square root of 81 to the first power, and I can break it down further from that. The square root of 81 is 9, and then 9 to the first is, well, just 9. In this example, we're going to rewrite the expression with exponent properties and simplify it further. So we will start with the power of a product property, allowing us to essentially distribute this exponent to both bases on the inside. So we would have 36 to the 3/2 power and x to the 4th raised to the 3/2. Now I'm going to start focusing on each base separately here. So I'm going to start by focusing on the 36. 36 to the 3/2 power, well, 3/2, if I rewrite it in the radical form, it's the square root of 36 to the 3rd power. The square root of 36 is just 6, and 6 to the 3rd power is 216. Now I'm going to go back up and focus on the variable x. This time we have a power raised to a power, so power of power property means that we're just going to multiply the exponents, so 4 times 3/2, which means I will be able to reduce this to just 2 times 3, which gives us x to the 6. And I'll just bring it down for the ride. So overall, we have 216 x to the 5th. Okay, so we're going to be simplifying this expression, which means no decimals here. If we take a look at it, starting with the number, 54 is not a perfect cube, so we're going to have to break this down. So, starting with the number, the numerical factor, I'm going to check what is the biggest perfect cube that goes into 54. Well, if I pull up a list of perfect cubes, so here's my list of perfect cubes, and just as a strategy to approach this, 54 would be between 27 and 64, so the first one I would check is 27. So is 54 divisible by 27? In other words, 54 divided by 27 is a whole number? Yes, it is. It is 2. So 27 is the perfect cube, the biggest perfect cube that goes into 54. If 27 had not worked, I would just move up my list, and if I get up here to 1, I wouldn't be able to simplify the cube root of 54, and it would just stay the same. But since 27 did go into it, I'm going to break the 54 down into 27 times, well, the remaining factor would be 2, so 27 times 2. Remember that as you break it apart, one of the numbers has to be a perfect cube, and preferably the biggest perfect cube, otherwise you'll have to keep repeating the same process over and over again. Now for the variables. The variables can only be broken down or simplified if their exponent is bigger than the index. So x squared here, 2 is a smaller number than our index of 3, so we're not going to be able to do anything with the x squared. However, y to the 6, we can. From the other from a previous lesson, we rewrote variables as a fractional exponent. So exponent over the index, so 6 over 3. 6 over 3 is a whole number, so y to the 6 is a perfect cube. So I'm not going to break y to the 6 down any farther. I'm just going to leave it as y to the 6. And as I go through this, I think I'm going to go back and underline my perfect cubes. Okay, there we go. And now we still have the z to deal with. Z, unfortunately, is not a perfect cube. It doesn't have an exponent that is divisible by 3. And it is also bigger than 3, so we will be able to break it down to some degree. So we're going to have to separate our z into two separate expressions. One with a power that will be divisible by 3, and one with a power that's just the remainder. So currently our exponent is 5. We want to ask ourselves, are there any numbers smaller than 5 that is divisible by 3? Well, there is only one that's smaller than 5, and that's 3. 3 is smaller than 5, but we still need a total of 5 z's. So if we're using 3 of them as our perfect cube, then we would need an extra 2 to add together and make a total of 5. Okay, so now that I have everything broken down, I'm going to go ahead and separate the stuff that are perfect cubes from the stuff that are not. So my perfect cubes are the 27. These are the ones that are specifically chosen. The y to the 6. And the z to the 3rd. The other ones I'm just going to leave in a single radical. They're just the leftover factors that we can't break down any farther. So 2 is the leftover numerical factor. X squared, its exponent wasn't higher than our index, so we can't break it down. And the z squared, which is the leftover from breaking apart the z to the 5th. To finish it, we just have to cube root each of these. The cube root of 27 is 3. The cube root of y to the 6, if I look at it as a fractional exponent, exponent over index, so 6 divided by 3 is y squared. For the z's, same thing, 3 over 3, 3 divided by 3 is 1, so z to the 1st. And then this expression, this radical over here, is my leftover factors that couldn't be broken down farther. They will just come down for the ride. So 2x squared, z squared. Finish up some side notes here. This is just a side note of a what if case. So for that z, we broke it up into z to the 3rd times z squared. If the exponent was higher, say z to the 10th, when we break it apart, we want a number smaller than 10 that 3 could have went into. So there are several different ways. Z to the 3 times z to the 7th, z to the 6th times z to the 4th, and z to the 9th times z to the 1st. However, when you're choosing the correct combination, just like when you're choosing the correct combination for the numerical factors, you want the biggest possibility. This way you can take out as large of a perfect cube as possible. So the combination we would use is z to the 9th times z to the 1st, because 9 is the biggest possible perfect cube that goes into z to the 10th. So we're always looking for the biggest thing that goes into it when we're breaking down the radical. Also, a second side note is remember that for simplifying radicals with variables, if this is an even index, you sometimes need absolute value bars around some of the variables, specifically ones without even exponents on the outside. So just be careful with the even roots. Okay, so here we go. We are asked what is the 5th root of 16 times the 5th root of 8 in reduced radical form. Well, to do this, when you multiply radicals, So notice multiplication. There's a couple things we need to check first. The first thing is that the indexes are the same. You can multiply radicals if they don't have the same index, but the process is a lot more complicated. It involves going into fractional or rational exponents. If they already have the same index, then it's much easier to multiply them. When you multiply radicals, as long as they have the same index, you simply multiply the coefficients and multiply the radicands. In other words, we multiply the numbers in front of the radical, not the index, but the coefficient, which in this case they are both 1 since there are no numbers there. And then we multiply the radicands, or the number underneath the radical. The index when doing the multiplication stays the same. So we would have 16 times 8, which is 128. After getting this, we just have to try to break down the radical now. Since it's a fifth power, we would look for the largest, or since it's a fifth root, we would look for the largest fifth power that goes into it. Okay, so off to the side, I have a list of perfect fifth powers. I stopped at 243, which is 3 to the fifth, because, well, that's already bigger than our number we have underneath the radical. So anything from 343 on won't be worth checking. So 32 is the only possibility, since 1 doesn't really help us simplify the radical. So if we check 32, 128 divided by 32, we end up getting 4. So we can simplify this radical. And we'll simplify it, or we'll break it apart into 32, which is our perfect fifth power, times 4. I'll continue to break this apart. We have the fifth root of 32 times the fifth root of 4. And I often skip this, writing that step out there. But to finish it off, the fifth root of 32 is 2, and we can't take the fifth root of 4, so we leave it like that. Okay, in this example, we are asked what is the sum of the square root of 20 minus 5 cube roots of 16 plus the cube root of 250 minus 2 square roots of 5. When you add and subtract radicals, you have to make sure two things are correct. First of all, in order to add and subtract radicals, they must have the same index and the same radicand. And then once they do have the same index and same radicand, you just add the coefficients, similar to combining like terms like 2x plus 5x. To get 7x, where the variable itself doesn't change. When you add and subtract radicals, the radical itself doesn't change either. So when we are simplifying sums of radicals, we first want to start by breaking down the radicals so we can see which ones have the same radicand. So starting with the square root of 20, 20 itself is not a perfect square, and the biggest perfect square that goes into 20 is 4. So I would rewrite it as 4 times the square root of 4 times 5, with 4 being my perfect square. The square root of 4 is 2, so 2 square roots of 5. The second radical I would do the same thing with. We do have that coefficient out in front. That doesn't really change much as far as the process. We have negative 5. We'll break the cube root of 16 up into, well, the biggest perfect cube that goes into 16 is 8. So 8 times 2. We have our negative 5 coming down. But the cube root of 8 is 2. Since the radical and the negative 5 are connected by multiplication, we will be multiplying the negative 5 and 2. Then we have left over the 2 that we couldn't cube root. We will have to multiply our 2 on the outside and the negative 5 on the outside, giving me negative 10 cube roots of 2. Forgot my index on the last line. Okay, the next one, doing the same thing. We have the cube root of 150. We'll have to again break it down. So the cube root 150 or 250 is not a perfect cube. However, 125 goes into 250, and 125 is a perfect cube. It's 125 times 2. The cube root of 125 is 5, so 5 cube roots of 2. And then as far as our last radical goes, it is the square root of 5, and 5 is not a perfect square, but there's no perfect squares besides 1 that's smaller than it that can go into 5. So this last radical is already broken down. So let's just go ahead and rewrite now that we've simplified each of the radicals. From the first term, we have 2 radical 5. From the second term, we have negative 10 cube roots of 2. From the third term, we have 5 cube roots of 2. It's a positive though, so plus 5 cube roots of 2. And then lastly, we have the radical that couldn't be broken down, are subtracting 2 square roots of 5. So we have successfully simplified each of the radicals. Now that we have done that, we can easily pick out like terms. So just working my way from left to right, we have a square root of 5. There is another square root of 5 down here, so we're going to combine them just by doing 2 minus 2. Well, 2 minus 2 is 0 and will cancel out. Sometimes terms cancel out, sometimes they don't, just like when you combine like terms with x's. Then we have negative 10, specifically the cube root of 2. We also have another cube root of 2. So we're going to add their coefficients. Negative 10 plus 5 is negative 5, and my cube root of 2 just stays the same. I can't do anything else after combining like terms, so this should just be the answer. Okay, in this example, we're going to be simplifying this expression. This is a binomial, or something with 2 terms, times a binomial, something with 2 terms. This is very similar to doing 2x plus 3 times x minus 5. The only difference is we have radicals here. But the general process is still the same. We just have to worry about how to multiply the radicals. So I'm just going to start by distributing. Keep in mind as I distribute, 4 radical 3 is all one term since there's no addition and subtraction there. So just like in the example I had with algebra, that 2x is all treated as one term. So we'd multiply that one time. Okay, so as we go through, 3 times 2 is 6. Nothing special about that. Then 3 times 2 radical 3. When you multiply radicals, you multiply the numbers out in front, the coefficients, and you multiply the numbers underneath. The 3 that I'm currently distributing is not underneath a radical, so it's only going to multiply the 2. 3 times 2 gives us a 6, and that radical 3 can't multiply with anything, but needs to come down, just like what we did with x's. Now I'm going to go through with the second term, which is negative 4 square roots of 3 times 2. So we'll multiply numbers outside the radicals. Negative 4 times 2 is negative 8. And since the 3 here doesn't have anything to multiply with, it's just going to come along for the ride. And lastly, we are doing negative 4 square roots of 3 times 2 square roots of 3. Multiplying the numbers outside, we get negative 8. But this time they both have radicals, so we also have to multiply the numbers inside. 3 times 3 is 9. The next thing we're going to do is combine like terms, but in order to do that with radicals, we want to make sure we break down the radicals first. So radical 3, square root of 3, we can't simplify. Square root of 3, we can't simplify. However, the square root of 9 is a perfect square, which is awesome. So perfect squares are great. Since it is a perfect square, the square root of 9 is 3. So that last term is going to become the result of multiplying 8 times 3. I'm just going to bring everything else down for now. 8 times 3 is 24. It's negative 24 because of the minus sign. After doing this, we just have to combine like terms. So 6 minus 24 is negative 18. And then we have a radical 3 and another radical 3. So 6 minus 8 is negative 2 square roots of 3. Remember, when adding and subtracting, the radical itself doesn't change, you just combine its coefficients. And as another reminder, this one happened to be a perfect square. They don't always have perfect squares. Sometimes that you have to break it down like you would on other addition and subtraction problems. It just depends on the particular problem. This is an overall process and not an exact step-by-step experience. In this example, we're going to be simplifying this expression. As we do this, when you simplify expressions dealing with fractions and radicals, our goal is typically to get rid of any radicals on the bottom of the fraction through a process called rationalizing the denominator. The way we do this is we multiply by 1. Now, multiplying by 1 doesn't change the value of an expression or a number, but it can change what it looks like depending on what one you multiply by. Since there is one term in the bottom, no addition or subtraction, what we'll do is we'll multiply by the square root of 5 over the square root of 5. Since the square root of 5 is the radical that's in the bottom, as I multiply by the square root of 5 over square root of 5, this is essentially 1 because it's a number divided by itself. This will also, when I do the multiplication, complete the square. So I will multiply at the top. 3 times radical 5 is 3 radical 5, or 3 square roots of 5. On the bottom, 2 square roots of 5 times square root of 5, or 1 square root of 5 if you prefer. Multiply the outsides, we have 2. Then multiply the insides, we get the square root of 25. We'll continue to simplify this. This should be a perfect square. If it's not, something's wrong and we have to go back and fix it. But the square root of 25 is 5. So in the bottom we have 2 times 5. On the top, sometimes you might be able to simplify this radical, sometimes you can't. In this case, the square root of 5 can't be broken down. It's not a perfect square. There's no perfect squares that go into it besides 1, so we leave it alone. And we'll multiply 2 times 5 to get 10. And at this point in this particular problem, we are done. There's one more thing you should try to check, and that's to see if there's anything that goes into the 3 and the 10. But there is nothing, so we can't reduce this fraction, and this is just our final answer. Now, in this example, we're going to be simplifying this expression, and there's a number of approaches we could take. But since the radical is around the whole thing, I'm going to start by writing it as 2 separate radicals. The square root of the top, 343, divided by the square root of the bottom, which is 20. In some cases, you may be able to reduce the fraction underneath the radical, and that can help the problem, help make the problem a little bit simpler. In this case, we can't reduce it, so I'm just jumping over that. Now, I can also do something here. I can also try to break down the radicals. In some cases, that might make the problem easier. In some cases, it might not. In this case, I'm just going to go for it. I'm going to try to break down the radical here. I believe 343 is not a perfect square, but I do know it's a perfect cube. So I can rewrite 343 as the square root of 49 times 7. And I can also break down the radical on the bottom. While 20 is not a perfect square, I do know 4 goes into 20. 4 is a perfect square. And 4 times 5 gives me 20. So if I do this, I'll be able to break down my radical, turning it into 7, the square root of 49 being 7. Square roots of 7 over the square root of 4 is 2, so 2 square roots of 5. So that makes the numbers smaller and a little bit easier to work with. After this, I will have to rationalize the denominator because unfortunately, simplifying the radicals did not get rid of the radical in the bottom of the fraction. Since there's only one term in the bottom, I will multiply by just the radical over itself, so radical 5 over radical 5, giving me, well, 7 radical 5, or 7 radical 7 times the square root of 5 is 7 square roots of 35. And on the bottom, we have 2 square roots of 5 times the square root of 5, so 2 square roots of 25. Square root of 25 is a perfect square, and it should be. If it's not, something is wrong. Square root of 25 is just 5. On top, sometimes this radical can be simplified, sometimes it can't. In this case, the square root of 35 is not a perfect square, and there are no perfect squares that go into 35 except for one, so we can't break down that radical. So 7 square roots of 35 will stay the same. If you could break it down, you should. Now we still have to multiply our numbers in the denominator. 2 times 5 is 10. So we have 7 square roots of 35 over 10. And lastly, we just have to check to reduce the fraction. Is there anything that goes into both 7 and 10, which are the numbers outside the radicals? There is not, so this is just our final answer. If there was something that goes into both numbers, for instance, 2 square roots of 5 over 6, 2 would go into both of these numbers, so we would divide both of them by 2 and reduce the common factor. However, that's not the case in this problem. Okay, this example is a souped up version of what we just looked at. So, going through, I'm going to start off by separating it into 2 separate radicals since the cube root is over the whole fraction. So I'm going to rewrite it as the cube root of 5 over the cube root of 9x squared. Now this one's a little bit different because it is a cube root instead of a square root. So I'm going to have to work about this one in a little bit different fashion. I can't just multiply by the radical. My goal here needs to be to multiply by something that's going to make it a perfect cube so that we can get rid of the radical in the bottom. So it's going to have to be a cube root that we're multiplying by. And if we think about the operations here, we need to figure out a number that 9 can go into that's a perfect cube. There's a couple different numbers that it could go into. For instance, 27. 9 goes into 27, and 27 is a perfect cube. 9 also goes into 729, which is actually 9 to the third. So I could choose either of these among other numbers. Usually, though, it's easier to take the smallest one possible. Having a bigger number will just give us more work in the long run with reducing the fraction. So now that I've decided to go with the 27, 9 goes into 27. So what do I need to multiply 9 by to make it this perfect cube of 27? Well, I know 9 times 3 is 27. If you don't know your multiplication tables real well, you can do 27 divided by 9 and get 3. And you can kind of do the same thing with all the other numbers until you find one that actually works out. But I know that 3 is what I need to multiply 9 by to make it 27, a perfect cube. So I'm going to multiply the top and bottom so far by the cube root of 3. Now we're not quite done here. We also have this x squared. I need x squared to be a perfect cube as well. Currently I have 2 x's. In order for it to be a perfect cube, this exponent has to be divisible by 3. Well, I only need a single more x to make it x to the third, which is divisible by 3. So I'm just going to multiply by the cube root of 3x now. So this should complete the cube in the bottom of the fraction. On top here, the cube root of 5 times the cube root of 3x would be the cube root of 15x. Multiply the numbers underneath the radicals. And same thing in the bottom, the cube root of 9x squared times the cube root of 3x is the cube root of 27x to the third, multiplying the numbers underneath the radical. Now we just have to simplify the radicals. So on the bottom, it should be a perfect cube. 27 is a perfect cube. The cube root of 27 is 3. And x to the third is a perfect cube as well. If I write it as a fractional exponent, it's 3 divided by 3, which is x to the first. On top, we just have to go ahead and check to see if it's a perfect cube or if there's any perfect cubes that go into it. 15 is not a perfect cube, nor are there perfect cubes that go into it. And for the variable x, it's just x to the first. So that's not bigger than our index, so we can't break it down any farther. So this is it. Okay, in this example, we're going to be simplifying the expression 1 over 2 plus the square root of 5. Now, if we were to try to take the same approach we did in previous examples, just by multiplying by the radical on top and bottom, this is going to cause an issue. Because if I do this, just focusing on the bottom for just a second, and distributing it through, I would have 2 square roots of 5 plus the square root of 25. While this is a perfect square, this will not be, which means I still have a radical on the bottom. So when there are two terms in the denominator, just multiplying by the radical itself is not going to cut it. So we have to multiply by something else, and it's a thing that we've used a couple times in Algebra 2 called the conjugate. So what we'll do is we'll multiply by the conjugate of the bottom. So 2 plus radical 5 is the current expression. So the conjugate of 2 plus radical 5 is 2 minus radical 5. So we're going to multiply that on top and bottom, which means we're essentially multiplying by 1, just a very special one. Now it's just two simple multiplication problems. We will distribute. We don't really have to distribute 1 through, but any other number we would. So it would be 2 minus square root of 5. On the bottom, these two are conjugates, so all we need to multiply is first times first. 2 times 2 is 4. And positive radical 5 times negative radical 5, which is negative radical 25. We're going to have to try to break down our radicals. The square root of 5 is not a perfect square, and there's no perfect squares that go into it, so I won't be able to do anything with the square root of 5. So it's going to stay 2 minus the square root of 5. On the bottom, however, the square root of 25 is a perfect square, so the square root of 25 is 5. So on the bottom, we have 4 minus 5, which is negative 1. Now we do have to finish it off. Normally, in a lot of problems, you would check to see if anything goes into all three coefficients here, all three numbers. There's not anything in this case. However, negative 1 is not typically left on the bottom of the fraction. Instead, we would divide each of these numbers by negative 1, just so that negative 1 isn't in the bottom, or any negative, for that matter, is in the bottom. So if I divide each of them by a negative 1, I would get negative 2 on top, then positive radical 5 over positive 1, after dividing each of them by negative 1. And since positive 1 is the only thing left in the bottom, we don't need to keep it because it's automatically implied to be there. So overall, the simplified version is negative 2 plus the square root of 5.